Let's talk more about derivatives. In this video, we're going to talk about finding the derivatives of the exponential function y equals e to the power of x, the derivatives of the general exponential function y equals b to the power of x, the applications of the exponential function, as well as the derivatives of sine, cosine, and tangent. Let's start by finding the derivative of the exponential function and building ourselves up. First of all, what is an exponential function? An exponential function is a mathematical function where the argument is denoted as an exponent. Many mathematical relations in the world are nonlinear. One type of nonlinear model we use is the exponential function. Exponential functions are used to model rapid change, such as compound interest, population growth, and radioactive decay. We will talk more about the applications later. For now, we will go over some examples of the derivatives of the exponential function. The problem we are given is fx equals e to the power of 3x. To find the derivatives, we will need to use the chain rule. Rewriting our expression, we will bring down the exponent and find the derivative of it, which is 3. Multiplying them together, we get 3e to the power of 3x. The reason that the initial exponent value doesn't change is because of a special property of the exponential, that the slope of a tangent at a point is the value of the function at this point for an exponential function. In general, if fx equals e to the power of gx, then f prime x equals e to the power of gx times g prime x. Here's another two examples. Let's go over the first one to begin with. The problem we are given is gx equals e to the power of 2x minus x. To find the derivatives of gx, we need to use the chain rule again. Rewriting the expression, we bring the exponent down to find its derivative. Multiplying them together, we get our answer. For the second example, we will have to use the product rule to find the derivative as they are multiplied together. Once we have our expression written down, we can find the factor, which is e to the power of x. Factoring e to the power of x gives us our answer f prime x equals e to the power of x times 2x plus x to the power of 2. Here's another example. Fx equals e to the power of x divided by x to the power of 2. You can use either the product rule or the quotient rule to solve this question. As the product rule was used in the previous question, we will be using the quotient rule to demonstrate. So, using the quotient rule, it's going to be x to the power of 2 times e to the power of x minus 2x times e to the power of x divided by x to the power of 2 to the power of 2. We can simplify this new expression by adding the exponentials of the denominator together to get x to the power of 4. Then we can factor out x and e to the power of x since they're common. This leaves us with the answer e to the power of x times x minus 2 divided by x to the power of 3. Now that we are familiarized with the exponential function and how to find its derivative, we can move on to the general exponential function. Finding the derivative of the general exponential function is not so different from finding the exponential function. Consider the following example. We are given the problem fx equals 5 to the power of x. The derivative for a general exponential function is generally fx equals b to the power of x, f prime x equals b to the power of gx times g prime x times ln b. Like the exponential function, the expression is rewritten with the derivative of the exponent, but this time also with the ln of b. This method can also be used to differentiate exponential functions with e, but as the ln of e is 1, there is no need to ln. To solve this example, we can rewrite the expression and bring the power of x down to find its derivative, which is 1. Then for the next step, we'll need to ln 5. This gives us our answer, ln 5 multiplied by 5 to the power of x. For the next example, we're given the problem fx equals 5 to the power of 3x minus 2. Our first step is once again rewriting the expression before bringing the exponent down to find its derivative. Once that has been accomplished, the base can be ln to give us ln 5. The answer will be 3 times 5 to the power of 3x minus 2 times ln 5. Now, let's get to some of the applications of finding the derivative of exponential functions. In this example, we're trying to find the effectiveness of studying for an exam. Depending on the hours t a student studies, they will get a result e. This is represented by the expression et equals 0.5, 10 plus te to the power of minus t divided by 20, where a student only has a maximum of 30 hours for studying. We are trying to find out how many hours would be the most effective for studying. To solve this example, we will have to find the derivative of the expression first. We can bring the exponent of the outside to the front, which will leave us with just 0.5. Since we need to use the chain rule, we'll find the derivative of the numbers inside the parentheses as well. After that, e to the power of minus t divided by 20 can be cancelled out, leaving 0.5e to the power of minus t divided by 20, parentheses 1 minus t divided by 20. Further simplification can be done by multiplying t and minus 1 divided by 20 together, giving us the derivative of the original expression. Equaling the new derivative expression we just derived to 0 allows us to find the maximum hours of studying that would give us the most effective result, which is 20 hours. Plugging it back into the original expression, we can find the effectiveness of E. We will also investigate how to determine the derivatives of y equals sine x and y equals cos x briefly. The general formula for finding the derivatives of sinusoidal functions is d divided by dx sine x equals cos x, and d divided by dx cos x equals minus sine x. We'll use the rule we just learned to determine the first derivative of y equals cos free x. When you find the derivative for cos, we know from previously that the derivative for cos is minus sine x. Using the chain rule, we bring the free x out and find its derivative, which is free. This leaves us with the answer minus free sine free x. Here's another one. We need to find the derivative of y equals sine to the power of 2x. Since y equals sine to the power of 2x equals sine x to the power of 2, we can use the chain rule to find the answer, which is 2 sine x cos x. As a parting note, we can briefly go over the derivative of tan. The general formula for finding the derivative of tan is d divided by dx tan x equals sec to the power of 2x. We find the derivative of tan the same way we find the derivative of sine and cos. Here we can see we need to find the derivative for y equals tan parentheses x to the power of 2 plus 3x. We can first start off by using the chain rule when finding the derivative. This gives us the answer 2x plus 3 sec to the power of 2 parentheses x to the power of 2 plus 3x. When determining the derivative for y equals sine x plus tan x to the power of 4, we can start off by bringing the 4 forwards and subtracting the exponent by 1. Using the chain rule, we can find the derivative of the values inside the parentheses, which will give us the answer. Throughout this lesson, we have learned how to find the derivative of exponential functions, derivatives of general exponential functions, applications of the exponential functions, and the derivatives of sinusoidal and tangent expressions. This is it for the video. Thanks for watching.